Hello, everyone. I know I just took myself off the camera. You don't need to see me. Y'all don't want to see that. Turn on my closed captioning. All right. So, uh, welcome. So today we'll be covering chapter 6, which is problem solving. Be a quick lecture. Just gonna go over a few things when it comes to problem solving. Share my screen. Alrighty. So problem solving, chapter 6. See if I can turn on. Bear with me. That's what they say. All right, there we go. Now we're cooking. Yeah, problem solving. So when it comes to problem solving and as an engineer, it's sort of like when it comes to designing, the first thing we said was identify the need. But in this case, because you're students, you're going to obviously identify the need. But what is the need? Well, it's what is needing to be resolved within that problem that is being presented to you. But I like the way another book presented it. It says, define the problem. Define the problem. Now, in most cases, if I give you a problem, the problem's already defined. And if you think about designing within that particular problem, they are asking you for something specific, right? And so you're not defining the problem, you'll redefine the problem by asking what it is that they're looking for. What are they looking for within this problem, right? Now, there are various problem types, and I know you all saw the slide. The variation of topics or problems is you have a ratio problem, you have an approximation. We talked about estimations in the last lecture. Estimation or approximation, getting a quick answer through estimating and simplifying assumptions. Parametric, the effect of multiple inputs on one or more outputs. And then ideal problems, those are the ones we really like, right? Calculating a quantity from a known formula, those are easy sometimes. And then you have discussion, determining important decisions, parametrics and relationships, or rationale rather. Which I guess you can also say relationships. But when it comes to problem solving, there are various approaches to each of these problem types, right? And so for this lecture, we want to talk about the approach, not so much the type, but the approach to problems. Now, I already gave you one thing to do, or one thing to do in an approach, which is defining the problem or identifying what the problem is asking, right? Identifying what the problem is asking. All right, and after you identify what the problem is asking, you want to make a list of your knowns and your unknowns, right? You make a list of your knowns, you know this, and then you make a list of what you don't know. All right, and then from there, step 2 would be simplifying the problem. Simplifying the problem. What does that mean? Simplifying the problem simply means is what are your assumptions? Once you have a good idea or a good understanding of the problem, you should ask yourself this question. Can I simplify the problem by making some reasonable or logical assumptions? right? Remember we talked about estimations. Can I make some assumptions, right? Can I make some engineering assumptions? Not just assuming and there are not anything. It's the assumptions that you're making are from things you have experienced in the past. You know, like if you are having a fraction and then an engineering assumption is saying this fraction will go into this number so many times to the power, right? Now, that's an engineering assumption, but it is also a logical or reasonable way to simplify a problem, right? But that's just one example, all right? That's just one example. But after you simplify the problem, the next step would be to, perform the solution, perform it. Whether there is a formula, input the numbers into the formula, or if it isn't a formula, if it's a ratio, grab that formula, create a ratio, uh, uh, set it up in the form of a ratio, right, to solve whatever the unknown is. And then after step 4 would be verify the results. Verify the results. That would be the last step. But let's break it down even further, right? So then, because when it comes to solving problems, in this, there's an acronym called SOLVE, right, within the book. Please read chapter 6 within your book. But I'm not going to go over all of this, but what I'm going to do is give you something. Because initially, I want you to merge these two things. Initially, I said defining the problem or identifying what the problem is asking, right? And then the first step here is to make a sketch. Make a sketch, right? Now, I would say, before you made a sketch, I would say identify what the problem is asking you. 1, 2, make a list. Because see here, it says list third. I'm saying make your list second. Identify what is needed. Write it out if you have, right? Write out what the problem is at. The problem is asking me to solve for this. Whatever this is, it could be a force, it could be a voltage, it could be a radius, it could be an area, a volume, it could be a multiplicity of things. But after you identify what the problem is asking, you make a list of what you know and what you don't know. All right. Which could also be observations and objectives, right? So after you make your observations and objectives, then make a sketch, or what we like to call as an engineer or a physicist is make a free body diagram, right? A free body diagram, which is simply a sketch of or a drawing of what's happening to that particular object within the problem. Now, it may not even call for a free body diagram, right? Especially if they're giving you a simple problem as an idea problem, which to just ask you for quantity, right? Using a formula, like find x if y is equal to x squared plus 4, and then they give you a list of numbers to plug in for y, or even vice versa, solve for y, and they give you a list of numbers to plug in for x, and they give you that equation, right? Which is an ideal problem. You won't have to make a sketch, you know what I mean? So I'm saying this, there may not be times where you need to make a sketch or a free body diagram. Sometimes you're just gonna be identifying, listing, right? And then plugging constants into your equation and then solving it, right? There are a lot of cases like that, which are ideal problems. Now, obviously, we don't have ideal problems in every situation because there are cases where it's not an ideal problem. Let's see. Let's find an example. Let's look at this. See how we can. This is a ratio problem. If I can find a good example. Nope, just got those two. All right, so, well, this is a ratio problem. Well, we can look at it anyway. All right, so this is really just a plug-in But we could look at example one. I'm sorry. Let's just look at example one. Okay. So again, this is an ideal formula problem. And the thing is, what it's asking, it says, what is the area of the largest equilateral triangle that can be cut from a circular piece of material of 50 centimeters in diameter? All right. 50 centimeters in diameter. Now, this is what that looks like. So it says, what is the area of the largest equilateral triangle that can be cut from a circular piece of material 50 centimeters in diameter? Now, you would draw that circle, obviously, and then you would make the diameter 50 centimeters. You would just label it that, right? We would label it that. Then you would draw a triangle from corner to corner. All right. And it says, the question is, what is the largest area of equilateral triangles? Now, if you all draw like me, that could vary. I mean, that could vary, but you're going to possibly need some type of a formula in order to do this. So you do know angles though, right? So if you draw a line there, and then at the bottom, if it's a 60, right? 60, right? And then 60 because it's equilateral. So all of these angles must be 60, which gives you the full degree of the triangle to be 180, right? 180. And then you're just using equations, to solve this, right? So the objective, determine the area of an equilateral triangle inscribed in a circle, all right? Your observations, each angle of the triangle is 60, 60, 60, 60. Total is 180. Each side of the triangle is a chord of the circle, all right? So this side here, your height is h, right? So each side of the triangle is a chord of the circle, all right? All right, the angle subtended by one of the chords is 120. So if you draw a line to the center of this triangle, then to the direct point to either side, either this side or that side, we know that this angle created is going to be 120. Now, the way you could check yourself is, this angle is 60. So if I cut this angle in half, and I have 30 here and 30 here, right? I know that this angle here is going to be 30 as well. So 30 plus 30 is 60. So this angle here would have to be 120. All right, so that's what we get there. Now, we know the diameter is 50 centimeters. So we know that we know the radius. All right, we know the internal equilateral triangle angle. We know the angle subtended by the chord is 120. We know the length of the chord. We know the height. We don't know the height. We don't know the length. And we're looking for the area. All right. So this is us listing our knowns and our unknowns. But previous to that, this is us creating a sketch. These are the observations that we make. All right. And the objective is, again, identifying what it is that the problem is asking us to do. We got to identify. And that is determining the area, right? All right. So now that we've listed what we know, now what we do, we can not just list what we know, we can also, come up with, we could write down formulas that we know, right? Right, we know the radius is half of the diameter. The area of a triangle is half the height times the length. The length of the chord, right? And this is a little bit of Pythagorean theorem, is equal to 2 times the radius times sine theta over 2. All right, and so, tan phi, the length of the opposite side, divided by the adjacent side, which is equal to height divided by the length over 2. So these are all known formulas that we can look up. All right, and then you solve for L because you have more than one equation, which you got 1, 2, 3 unknowns, so you need 3 equations, right? You come over here, you have equation for the area, equation for the length, equation for the height. 3 unknowns, 3 equations. Then you solve for L, which is 1.73 times the radius. Plug that in into the height, right? And after that, you know H is equal to 1.5 times R. Plug that in for your area. A is 1.3 times R squared, and we know what R is. So from there, you're just plugging in what you know into what you don't know to solve for one of your unknowns. And now that we've solved for that, we could go back and solve for the other 2 unknowns, but that's not what they asked for. They only asked for the area. All right, and that's the approach. The approach to solving a problem. I won't go over example 2. It's fairly simple, so I'll just leave that for you all. Again, another quick chapter, another quick lecture. And if you have any questions, please feel free to email me. Thank you all for listening, and that's my time.